Hi, everyone. There's a pretty tricky problem on the homework this week, so I thought I would record a video and at least help you set up the geometry. So this is what the problem sort of looks like. It says you take a radius r sphere, so capital R gives you the radius of that ball, and you want to drill a hole of radius little r, which I have right here, down through the top of the sphere. And when you're done, that hole will be sort of shaped like a cylinder and it will have height h. The question becomes, what is the volume of the sort of ring around it that's left over after you drill that hole? And the most natural way to compute this, well, there are two ways, I guess. You could use washers, but let's use cylindrical shells. So the idea is going to be something like, you want to fill this whole region up with a bunch of cylinders, right? And I'll just sketch some quick examples. There's a cylinder inside of the filled in region. Here's a really wide cylinder inside the filled region. Here's a sort of middling cylinder. And it gets very cluttered very quickly, but you're just trying to fill up this region with cylinders. Cylindrical shells, I should say. And so the idea comes out to be something like, you just want to compute the volume using the standard integral formula. Volume equals the integral from something to something of 2 pi. And then here you can put the radius of those cylinders that I was drawing. And then here you can put the height of the cylinders. Let's say we use the variable x, so I'll write dx. The first thing to answer is, what are my bounds on this integral going to be? And that one shouldn't take too much thinking beyond the picture I just drew, in the sense that, you know, the smallest cylinder you can fit in is basically this yellow cylinder of radius little r. So it's going to look like, well, my smallest cylinder has radius r. My biggest cylinder looks like it has radius capital R, right? Because that would be like a really short but wide cylinder hanging out in here. That would be the other extent. So, okay, you might think the integral goes from little r to big R, and you'd be right. As usual, this is just going to be the radius you can just write as x. Right, this region's basically a solid of revolution. If you wanted to, you could draw axes in here and say, you know, this is the y-axis, this is the x-axis. I revolved, you know, I guess this region about the y-axis, and as such, you know, the radius doesn't have to be very complicated. It can just be x. But then one of the tricky things is going to be, what is the height of such a cylinder? Right, so let's just get one cylinder in here. What would the height of such a cylinder be? Namely, what is like this distance here? And this requires a little touch of geometry. In particular, you know, you might want to find out what this blue function is. Right? Could I write a function like y equals some function of x for that blue curve? And then the height would just be sort of double that y value. But this diagram's sort of cluttered, so let's go down a bit. Let me actually move this up. So we'll get this all in one screen. Maybe I'll go over here. So the reasoning is going to be something like, okay, here's a straight on view, right? Instead of having it all three-dimensional, I'm just saying, okay, this is, you know, this yellow stuff is representing the cylindrical hole that we cut. Technically, there's like no top anymore to the cylinder, but whatever, pretend it's still a circle or a sphere to start out with. Then what we can do, let's just zoom in on the first quadrant here. So positive x, positive y. What I want to do is I want to find an equation for this curve. Now, it certainly looks like it's just a chunk of a circle with radius r. So you might say, oops, wrong tool. You might say, okay, well, this is a circle of radius r. I can write that as x squared plus y squared equals capital R squared. But in particular, it's sort of the top half, right? So if I wanted to solve this for y, I could do that the usual way. So y squared would be that. And then when I take the square root, I get either plus or minus square root big R squared minus x squared. But we said it's the top half, so it should be the positive half. So let's just treat it as positive, this square root. Okay, so that's a perfectly good function-y way to write what this blue curve looks like as a function of x. And so indeed, you could say, well, for this, let's draw one of my white rectangles in here, or white cylinders that I'm going to draw as a rectangle because it's a two-dimensional slice I'm looking at. If this was this particular x value, right, we were integrating x from little r to big R. So this is some intermediate slice for this cylindrical shell. Then the corresponding height of at least this chunk is going to be exactly big R squared minus minus x squared under a square root, right? So that could go here, meaning the height itself should be double that, right? So I could say that means that, going back up to this formula, the height here, I probably need to make this a little wider, should be exactly twice the distance to the function. Like so. Just double this. Okay, so that's how you set up your integral. Of course, you can simplify some things, right? You can pull out the 2, you can pull out the 2 pi, write this as, I guess, 4 pi, still integrating from little r to big R, and just x times this square root. Now I'll let you guys do the calculus, right? Eventually you can determine an answer here. There are some tricks we know that we can apply, and it's not too bad. But the problem statement actually says that we want our answer in terms of h. Notice there's no h floating around yet. H, you will recall, is the height of the drill bit, right? The hole that the drill bit cut through the sphere to start with. So we want to get it in terms of h. That presents a slight problem, but we can handle that using this same diagram. What you want to do is something like this. So let me just sketch this again over here so we have a fresh graph. Let's say, our function goes to here. Try to draw this. That's the little arc of the circle from right here. And it turns out that this will be h over 2. That's sort of half the height of the hole that got cut. And just for the sake of argument, let's still call this x. So we have some little cylindrical slice that we're cutting at that x value. Okay. I'm not going to show you everything to do here, but I'll give you some big hints. In order to get your answer for this integral, in terms of h, you're going to need to know a couple things. Let me write on here that this distance is still r. And in fact, you can draw a little diagram. This distance is still little r. Actually, I probably don't need the x, so let's just clean up the diagram and not show x. let's just use this. I think that should be enough. So what we can do here to get h in terms of big R and little r, or vice versa, is I could probably find some kind of triangle to draw in this region. So a good triangle to draw, I mean, we have, I guess, a couple options, but let's pick a nice one. So let me scoot this aside. Let's actually put this over here. Just move it over. So a nice triangle to draw would be this. There's a right triangle. I know that this side is just little r. So let's just move that over to here. I have that the yellow side is h over 2. And for the same reason that, this distance is big R, so is this distance, the hypotenuse here. Right? It's like a circle, it sweeps out the same distance the whole way. So I can put here capital R. So from this, you can write down, the Pythagorean theorem, THM for theorem, and this just says that the hypotenuse squared should be one leg squared plus the other leg squared. Okay, so this is just a piece of the puzzle. Obviously, I'm not showing how it fits into the calculation, but I promise that if you actually go through and figure out this integral, you'll get some expression. You'll get something here that, involves maybe an r squared, a little r squared, something like that. And using this relationship, you should be able to translate this answer that you got here exclusively in terms of h. You just have to make use of this nice fact. So doing that should get you the right answer. It's mostly algebra at that point. But there you go. It's sort of fascinating, actually, that the volume of this weird shape that gets cut only depends on h. It doesn't depend on the radius of the circle you started with or the radius of the drill bit you used, just h. Super weird, but yeah, I hope that helps. Feel free to come to office hours or email me if you're missing some little details that turn out to be important. But otherwise, good luck. Thanks for watching.